At 04:08 on November 5, 1983, aboard the semi-submersible drilling rig Byford Dolphin, a routine pressure transfer between a diving bell and a saturation chamber system failed during a standard operational sequence. The event lasted less than 1 second and resulted in 5 fatalities. The rig was operating in the North Sea above the Frigg gas field, where saturation divers were conducting subsea maintenance at a depth of approximately 300 feet, a pressure environment requiring specialized life support systems. Nothing exploded, no structural component collapsed, and environmental conditions were stable. The failure occurred inside equipment that had been functioning normally and had been designed specifically to prevent rapid pressure loss. Inside the system, internal pressure measured approximately 9 atmospheres, equivalent to the surrounding water pressure at working depth. Outside the system, pressure remained at 1 atmosphere. The difference between those pressures was contained by a sealed mechanical connection joining the diving bell to a transfer trunk attached to the chamber complex. That connection was secured by a hydraulically actuated clamp designed to resist the outward force generated by compressed gas pressing against the interior surfaces of both vessels. Saturation diving exists to avoid repeated decompression. Divers are pressurized once, remain under pressure for days or weeks, and decompress only at the end of the assignment. They live inside steel chambers, maintained at working depth pressure, and travel to the seafloor in a sealed diving bell that preserves that pressure environment. This method reduces physiological stress from repeated ascents, but it concentrates risk into a single continuous pressure boundary that must remain intact at all times. At the time of the transfer operation, the personnel inside the pressurized system were Edwin Coward, Roy Lucas, Björn Bergersen, and Truls Hellevik, all trained saturation divers assigned to the shift. The dive tender responsible for external equipment control was William Crammond, positioned beside the chamber assembly where he monitored gauges and operated hydraulic controls. Immediately prior to the incident, all system readings were normal, and there were no warnings or malfunctions indicating that a catastrophic failure was imminent. The transfer sequence required the bell to be raised from the water and positioned precisely beneath the chamber assembly, where alignment guides ensured correct mating between the bell flange and transfer trunk. Hydraulic clamps were engaged around the mating flanges, compressing a sealing gasket designed to prevent leakage once pressure equalization began. Only after full mechanical engagement was confirmed could the trunk pressure be adjusted to match the pressure inside the bell and chamber. When pressures matched, internal hatches could be opened safely, allowing divers to move between compartments without exposure to atmospheric conditions. The order of operations was critical: clamp engaged, pressure equalized, hatch opened. Only after isolation could the clamp be released. Releasing the clamp while pressure remained inside would expose the system to full differential force, converting stored compressed gas into a violent mechanical event. At 04:08, the clamp securing the connection released, while the system remained fully pressurized, allowing the structures to separate and exposing the interior atmosphere to open air. The pressure differential measured approximately 8 atmospheres, equal to more than 100 pounds per square inch, acting across every exposed surface once the seal failed. The decompression occurred in less than 1 second, a rate so rapid that the human nervous system cannot consciously perceive the change before physiological damage begins. Hellevik was positioned inside the transfer trunk when separation occurred and was subjected directly to the mechanical force generated by instantaneous pressure equalization. Investigators determined that the forces involved exceeded the structural limits of human tissue, and medical findings concluded that death occurred immediately at the moment of decompression. Coward, Lucas, and Bergersen remained inside the adjacent chamber compartment when the trunk depressurized, and because the hatch between compartments was open, the chamber atmosphere vented through the same opening. The resulting pressure drop occurred too rapidly for physiological compensation, causing dissolved gases within their bodies to expand throughout the circulatory system and internal organs. Autopsy reports concluded that death resulted from explosive decompression and massive gas embolism, a condition in which gas bubbles obstruct blood flow and prevent oxygen delivery to the brain. Outside the system, Cramond was standing near the clamp assembly when separation occurred and was struck by heavy structural components released by the sudden force of decompression. He sustained severe traumatic injuries and died shortly afterward, despite immediate assistance from nearby crew members. Investigators reconstructed the timeline using physical evidence and equipment analysis, confirming that clamp release preceded all other mechanical events and initiated the decompression. Inspection revealed no structural fracture or mechanical defect, indicating that the securing mechanism had been activated while pressure remained inside the system. Control panels allowed hydraulic release regardless of internal pressure conditions, and no mechanical interlock existed to prevent actuation when pressure differential exceeded safe limits. The investigation concluded that the accident was preventable and identified absence of a pressure interlock as the primary design vulnerability. Following publication of the report, international saturation diving standards were revised to require redundant barriers preventing pressure boundaries from being opened unless internal and external pressures were equalized. Modern systems now incorporate pressure-sensing lockouts and confirmation sequences designed specifically to prevent the sequence of events that occurred aboard the Byford Dolphin. Saturation diving continues to be used in offshore operations, but system design philosophy shifted after this accident to reduce reliance on flawless human performance. The physical mechanism is understood, the sequence is documented, the cause is established. The system functioned correctly until the moment it did not. The clamp system on the Byford Dolphin relied on hydraulic pressure to engage and disengage the securing arms that locked the bell flange to the transfer trunk. When engaged, those arms held the two pressure vessels together against outward force generated by compressed gas inside. At 9 atmospheres, the internal pressure inside the system produced thousands of pounds of force pressing outward across the connection surface. As long as the clamp remained engaged, that force was contained entirely by steel components. Once released, however, that stored pressure energy was no longer restrained, and the compressed gas inside the trunk and adjacent chamber expanded toward atmospheric pressure at extremely high velocity. The opening created by separation measured approximately 60 centimeters in diameter, just under 2 feet across, yet the effective force applied across that opening was equivalent to several tons. Explosive decompression differs from gradual decompression in both rate and effect. Instead of dissolved gas leaving tissues over hours or days, it expands almost instantly within blood vessels and organs. The rapid formation of gas bubbles disrupts circulation immediately, preventing oxygen delivery to the brain and heart and causing catastrophic failure of vital systems within seconds. Investigators determined that the time between clamp release and full pressure equalization was less than 1 second, leaving no opportunity for manual intervention once separation began. Witnesses on deck described a loud mechanical noise followed by the abrupt movement of equipment, but the internal event had already concluded before anyone could respond. The bell itself remained suspended by its lifting cable after separation, preventing it from falling to the sea, but the connection to the chamber system had been destroyed. Inside the remaining chamber, pressure stabilized at atmospheric level only after the violent venting process had concluded, and by that time, all 4 divers inside the pressurized system had died. Medical analysis confirmed that survival under those decompression conditions would not have been possible, regardless of emergency response speed or available treatment. The Norwegian Petroleum Directorate initiated a formal investigation shortly after the accident, focusing on equipment design, operational procedures, and the sequence of human actions that preceded the event. Physical examination of the clamp mechanism revealed no fracture, material defect, or hydraulic malfunction that would have caused spontaneous release under load. Instead, the evidence indicated that the release control had been activated while the system remained under pressure, initiating separation through normal mechanical function. The control interface for the clamp was positioned near other hydraulic controls, and the investigation examined whether layout design or procedural ambiguity could have contributed to inadvertent activation. While the exact reason for the release could not be determined conclusively, the report identified human error as the most probable initiating factor in the absence of mechanical failure. However, the investigation also emphasized that reliance solely on operator performance without mechanical interlocks represented a systemic vulnerability in the equipment design. The official findings concluded that a pressure-sensing interlock would have physically prevented clamp release while a pressure differential existed, eliminating the possibility of this specific failure sequence. In response, regulatory authorities required that saturation diving systems incorporate redundant safeguards, ensuring that pressure boundaries could not be opened until internal and external pressures were equalized. Equipment manufacturers subsequently redesigned clamp assemblies to include automatic lockout mechanisms tied directly to pressure sensors, removing the possibility that a single manual command could override pressure conditions. Operational procedures were revised to include additional verification steps and cross-check requirements during transfer operations involving pressure boundaries. The Byford Dolphin continued operating after the accident, and its saturation system was rebuilt in accordance with updated safety requirements before returning to service. The accident remains one of the most severe incidents in the history of commercial saturation diving and is studied in industry training as a case example of pressure boundary failure. The mechanism of failure is now fully understood, and the forces involved can be calculated precisely using established gas expansion equations and pressure differential models. The event demonstrated that complex industrial systems cannot rely exclusively on procedural compliance when the margin for error is measured in fractions of a second. In high-consequence environments, engineering safeguards must assume that human error will occur and must be designed to prevent a single incorrect action from producing catastrophic results. On November 5, 1983 at 04:08 hours, a clamp was released. The pressure equalized. 5 men died. The system functioned correctly until the moment it did not. After Byford Dolphin, pressure boundaries in saturation systems could no longer be opened while pressure remained. That design change is the legacy of what happened that morning. This has been Episode 2 of Echoes of Silence, a documentary series examining industrial and technological system failures. New episodes are released weekly.